Good morning, pre-calculus. We're going to start the next chapter, chapter 5. Chapter 5 is going to focus on rational functions. Going to do a lot of stuff with rational functions. You first saw these in Algebra 2, spent some time with them in college algebra, but they were tough and they were awkward. They've got a lot of applications. Most of the stuff from this chapter is stuff that we have an idea about, but as we get towards the end of the chapter, we will see some brand new things that we've never seen before. So this is the first part of the lesson from 5.1, Rational Functions and Asymptotes. We're going to talk about some things that hopefully we'll remember from the previous class and kind of set us up to looking more specifically at all the different types of asymptotes and properties of rational functions. All right, here we go. So first, very basic, what is a rational function? A rational function is, if I think about some sort of function f of x, it's going to be some polynomial over another polynomial. Now, we're going to focus just on rational functions that are nice, well-behaved polynomials over other polynomials. There is lots of other types of rational functions where you could have a weird square root or some crazy stuff here and there, and we'll deal with those separately. Now, the polynomial, definition of a polynomial, and this shouldn't give anybody a hard time, a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 all the way down to a sub 2x squared plus a sub 1x plus a sub 0. I ran out of space there. All over b sub m x to the m plus b sub m minus 1 x to the m minus 1 plus dot 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 all the way down to b sub 1x plus b sub 0. So the a's are the coefficients. A sub n minus 1, all the way down to a sub 0. A sub n is the lead coefficient of the polynomial in the numerator. A sub 0 is the constant of the polynomial in the numerator. B sub m is the lead coefficient of the polynomial in the denominator, and b sub 0 is the constant of the polynomial in the denominator. The n is the degree of the numerator, and the m is the degree of the denominator. These become very important later when we talk about the asymptotes. So there's a basic definition of an asymptote, of a rational function. And we've seen examples. We know what these things look like. For example, f of x equals something like 2x over x squared minus 9. And as soon as I write that, things should jump into your head. Things like the number 0 is going to be a problem. The number 3 and negative 3 are going to be a problem. And what happens in those areas? And we should have an idea. We should kind of remember that from our previous class, what's going on there. All right, so let's take a look at an example. And for the first example, all I want to do is talk about simplifying rational functions, because I want them in that form. I want them in the form of some polynomial over some other polynomial. So suppose I start with f of x is equal to, let's make this a kind of an ugly one here, 1 plus 1 over, I don't know, let's say x minus 1 over x. Oh gosh, all sorts of crazy things going on in this one. So this is a rational function, but it's not really in the form that I want. Clearly 0 is going to be a problem, but is there anything else that's going to be a problem here? I need to put this into standard form for a rational function. So follow some steps along with me here. I'm going to get 1 plus, if I multiply that by x over x, I've got 1 x squared minus 1 over x. And then, of course, I can take the reciprocal here, 1 plus x over x squared minus 1. This is the same thing as x squared minus 1 over x squared minus 1. So I'm going to get x squared minus 1 over x squared minus 1 plus x over x squared minus 1. Combining it all in like terms, writing in descending order, x squared plus x minus 1 over x squared minus 1. So now we've got it in nice simplified form. And we know from here x cannot equal 0. So down here, could I put in 0 in here? It seems like I can. It seems like I could put in 0 here and I'd get negative 1 over negative 1, which is just 1. But we still have this restriction. This restriction is still going to apply. And it looks like we picked up another restriction here. X can't be 1 or negative 1. But don't forget about this from the original polynomial, the way it was originally written. We have a domain restriction. X cannot equal 0. So we want to get it in this form. So now we can see we've got a nice, well-behaved polynomial. And we can see it's a second degree over a second degree, lead coefficient of 1 and 1, constants of negative 1 and negative 1. All of those things become important a little bit later. All right, let's take a look at a specific problem now, a specific example. So here's one that should be familiar to us. The parent function, f of x equals 1 over x. And as soon as we look at that, we should immediately remember what this thing looks like. If I just sketch a quick graph of this thing, it goes through the point 1, 1, negative 1, negative 1, and it looks like this, something like this. We know that we've got an asymptote at 0. An asymptote is that do not cross line. It's part of the domain restriction here. I put a dotted line there. X cannot equal 0. X equals 0 is an asymptote. This do not cross line. 0 is not part of its domain. I cannot plug in 0 there. But notice this is a vertical asymptote. This is a vertical asymptote. So let's designate that, because we're also going to talk about horizontal asymptotes in a minute, because I seem to have a horizontal asymptote here. As x's increase without bound, f of x is approaching 0, and as x's decrease without bound, f of x is also approaching 0. Let's just spend a moment talking about the definition of a vertical asymptote. Let's be a little bit more rigorous when we talk about these things. All right, so vertical asymptote. The line, the vertical line, x equals h, where h is just some constant, is a vertical asymptote of a function if, as x approaches h from the right or the left, f of x approaches positive or negative infinity. And remember, this is the way we say it, approaching infinity. I don't like that so much. Think about it as increasing or decreasing without bound. So this is the true definition of what a vertical asymptote is. And we saw it in the previous example. As the x values get closer and closer to that value, like in 1 over x, as it was getting closer and closer to 0, f of x was becoming infinitely large or infinitely small. In the case of 1 over x, it depends on which way you are approaching. All right, so let's take a look at an example now. We'll take a look at a function and kind of pull it apart and see what happens. Suppose I'm given the function f of x equals 1 plus 1 over x minus 1. So now as I take a look at this, the first thing that jumps out at me is x cannot equal 1. But it's not written in the right form, is it? I need to do a little bit of work on this thing. So 1 I know is the same thing as x minus 1 over x minus 1 plus 1 over x minus 1. Combining like terms, I can see the 1's are going to cancel here, and I get x over x minus 1. So here's my function in the right form. My numerator and denominator have the same degree. I still have the restriction that x cannot equal 1. That's going to be my vertical asymptote there. But I've also picked up the top here when x is equal to 0. What's going to happen at 0? If I plug in 0 for x, I'm going to get 0 over negative 1, which is just 0. So that becomes an x-intercept. And here we have a very important property. The zeros of the numerator become my x-intercepts. The zeros of the denominator are my vertical asymptotes. We should remember that from the Pre Calc class. If I go to, the college algebra class. If I go to graph this, I'm going to graph x divided by, in parentheses, x minus 1, close parentheses, on a standard viewing window. And we can see that I've got the asymptote here at 1, and we can see that it goes through the origin. When x is 0, y is 0, 0, 0. Plug in 0, and I get 0. So I've got a vertical asymptote. If I go to graph it, vertical asymptote, around 1 is when interesting things are happening. And I'm going to designate that as, that's my vertical asymptote. The function is not defined there. It has an x-intercept, and as I can see by the behavior, it looks something like this and this. Now it goes off the screen. I could ask the question, do you think it might be able to cross the x-axis at some point going either way? And the answer is no. How do you know for certain? Because the only x-intercept happens at 0, nowhere else. That's the only 0 of my numerator. The only place that it crosses the x-axis here is 0. The only place where it's undefined is at 1. So here's my vertical asymptote. X equals 1 is a vertical asymptote. But notice I seem to have some sort of horizontal asymptote there. And unlike 1 over x, it doesn't seem to be getting closer and closer to 0. It's not coming back down. What's it doing as it goes in either direction here? Well, this is where we have horizontal asymptotes. Let's look at the definition of a horizontal asymptote. A horizontal asymptote. It's going to be a horizontal line. So the line y equals k is a horizontal asymptote of the function if f of x approaches k as the x's get infinitely large or infinitely small. Increase without bound or decrease without bound. The function is approaching some constant k, some number k. In the line 1 over x, it was getting closer and closer to 0. In the previous problem, it seemed to be going closer and closer to something else. All right, let's take a look at an example of finding a horizontal asymptote. We want to identify the horizontal asymptote. I'm going to use HA for horizontal asymptotes and VA for vertical asymptotes of the function f of x equals, and I'm going to give it to you already in nice form, 2x plus 1 over x. And I want to find the end behavior. As x's get much larger and larger and larger, or as x's get smaller and smaller and smaller, what happens? Well, here I'm going to use polynomial division. 2x over x plus 1 over x. Breaking it up, and I get 2 plus 1 over x. Now what happens when x's get larger and larger and larger? As x's get larger and larger and larger, or smaller and smaller and smaller, what happens to this term right here? 1 over 10, 1 over 100, 1 over 1,000, 1 over 1,000,000, and so on. This term disappears. So I end up with just that line right there, the line y equals 2. That is my horizontal asymptote. Because as the x's get, this function is the same thing as this function, and as x's become infinitely large, that term disappears, and I'm left with just the line y equals 2. Let's take a look at this graphically. So take out your calculators, if you don't have them out already. Let's graph this function right here. So open parentheses, 2x plus 1, close parentheses, divided by x. Now that's all I'm going to graph at first. I'm going to go to standard viewing window, and Sure enough, just as I anticipated, it has the vertical asymptote. Oh, I didn't say that before, did I? I've got x cannot equal 0. That's actually my vertical asymptote at the line x equals 0 at the axis, and we can kind of see that now. And as x's approach 0, the function becomes infinitely large if I'm approaching from the right. As I approach from the left, as x's approach 0 from the left, it's becoming infinitely small, my basic definition of the vertical asymptote. But the horizontal asymptote, we can see that it's not approaching 0. I've got an x-intercept here too. How would I find the x-intercept? Well, if I plug in 0 here and solve it for x, which means set this equal to 0. 2x plus 1 equals 0, subtract 1, divide. X is 1/2. We can see that right here. I've got an x-intercept at negative 1/2. But it's this line that I'm interested in. Let's graph it on top. So I'm going to go to my y equals, go down to y2 and put the line 2 in there, and I'm going to graph it right on top. There's the line y equals 2. And I know it's not very large here, but let me pause for a moment, give you a chance to really take a look at this. Make sure you've got this in y1, this in y2, and just take a look at it, how the function's getting closer and closer to 2. As x's increase without bound, the function's getting smaller and smaller and smaller, but it's approaching 2. As x's decrease without bound, the function's actually getting bigger and bigger and bigger, closer to the line y equals 2, but from the negative part. But it never actually reaches 2. So this is my horizontal asymptote, the line y equals 2. So vertical asymptote and horizontal asymptote. All right, so I'm going to pause the lesson here at this point, and when we come back, we're going to look over all the asymptotes. We're going to look over all the different characteristics, review a bunch of stuff from the previous class, and then we're going to look at some specific word problem examples in the second half of this lesson. So if you want to pause for about 15-20 minutes, start the homework, take a look at it. Don't forget to turn on the next video and watch the next video. We need to get the whole video in before the end of the class, so there'll be part 2's coming up. I'll talk to you guys in a few minutes.